Right. Well, thanks, Michelle, for the introduction. Hello, everyone. So, again, my name is Amro, and indeed, I graduated from NC State almost 7 years ago. Then I was at different places, including UCF and Sandia National Labs before coming back during pandemic here. So, in case you haven't seen me in person, it's because of the pandemic mostly. So, today I'll be talking about high performance and the crash-recoverable security support for emerging memory architectures. So this work has been supported by multiple agencies, and whatever I will share does not necessarily represent their views or opinions. So the outline or the rest of my talk will be organized as follows. I will start with a group research overview. At high level, I will describe what my research team is looking at, the different problems we are exploring solutions for. Then I will get to the main topic of this talk, which is high-performance secure persistent memories. After that, I will briefly touch on ongoing research projects and directions, and finally conclude the talk. So at high level, my research team and I have been looking at topics including emerging memory systems. This includes emerging memory technologies such as non-volatile memories, stacked DRAM, etc., and how does integrating multiple types of technologies in computing systems complicate the performance, the management, the way how we expose data to programmers, etc. We have been also looking at how these new emerging memory technologies and architectures could complicate secure implementation or security support. And we have also been looking at even data center architecture, which is disaggregated memory systems and emerging system architectures, implications on access control implementation, performance, and memory management. We have been also recently looking at secure accelerators and in-memory computing. So with these type of accelerators that are emerging, how can we provide security support, including access control or data protection? And in some work we have been doing with Navy, we have been looking at the problem of deterministic performance. So if you have shared resources in your multi-core system or even heterogeneous compute system, how can you ensure performance isolation? This is important for certifying systems that run real-time workloads. So the rest of the talk will be focused on this particular part, and it's going to be on a very particular portion of these efforts, which is how can we provide security support for emerging non-volatile memory technologies? So next, I will be getting into the main part of this talk, and it will be organized as follows. I will give you a high-level overview of what do we mean by persistent memory or emerging non-volatile memories. After that, I will describe how typically hardware support for secure memories in general, whether it's volatile or non-volatile, is implemented. And after that, I will mention why it's challenging for combining both secure memory support and emerging non-volatile memories and our solutions towards this problem. And let's get there. So in today's computing systems, if you bought a server or in your laptop or even in your mobile device, there is a clear difference or a clear distinction between the main memory and storage subsystems. So the main memory is really the working space where you store your temporary data that your application is using, where your malloc or a new or allocation inside the application is happening. Typically, this is fast. When I say fast, this is tens of nanoseconds, but at the same time, it is volatile, which means that once you are unplugging the power cord from the system, basically you will lose the data in the main memory, which is the DRAM. On the other hand, you have the storage subsystem, which is your typical solid-state drive, your flash, etc. That one is where you actually keep your files or the data that you care about persisting across power outage events or system crashes. On the other hand, this is extremely slow. If you have ever measured the latency or looked at the white papers for some of these drives like flash or SSD, these are typically milliseconds or tens of microseconds. So there is this clear performance gap between the storage subsystem and the main memory. On the other hand, the storage subsystem provides an additional characteristic, which is the data persistence feature. On the other hand, the DRAM allows you actually to have fast memory access, but at the same time, it does not provide you with the ability to retain data across power outage events. So if you have a file, you want to store it, you will not put it in your DRAM, but rather you will put it in your storage subsystem. So fortunately, there are technologies, which we call them emerging non-volatile memory technologies, that bridge the gap between these both storage subsystem and main memory subsystem. So emerging non-volatile memory technologies provide you with fast access times and also durability, which means that you can keep your data there for a long time. Even if there is an event of power outage, your data actually will still be retained. So this will allow us to have persistent memory, which allow your data to survive events of power outage and crashes. Examples of these technologies includes phase change memory, ReRAM, and STT-RAM. So a little bit more about persistent memory or emerging non-volatile memories. And before I get into the details, persistent memory is just a description of a memory that can retain data in systems when events like power outage or crashes happen. So realizing persistent memory does not necessarily need non-volatile memory or emerging non-volatile memory. You could have battery with DRAM to back it up to flash, etc. But one of the ways that you can realize persistent memory with is emerging non-volatile memories. If you have ever seen, any one of you have ever had 3D cross-point memory module? Anyone here? All right, so I had one. So it's looking like this exactly here. It is much denser than your typical DRAM. So some of these modules we had in our lab actually is ½ terabyte, so just the module. If you want to relate this to DRAM, your typical DRAM module is 8 gigabyte or 16 gigabyte. On the other hand, it also enables crash consistency, which we know since it's non-volatile, but it features ultra-low idle power. So if you have looked in detail on DRAM technology, you would realize that DRAM cells have to be refreshed every 64 milliseconds or so. So even though you might not be using all your memory module or DRAM, you still need to frequently refresh the cells, which means you read them and rewrite them. Recent studies from Google data centers have shown that this can contribute to 40% of your total power, just refreshing the DRAM cells. So emerging non-volatile memories promise great reduction for the idle power of your memory system. Example of these technologies, again, include ReRAM, phase change memory, MRAM, and fortunately, there is healthy competition and ecosystem where different companies are exploring different use cases and different technologies for these NVMs. The challenges for using these non-volatile memories include security. So if you think about it now, you have your memory containing the data forever. So if you lost your laptop, your mobile, etc., anyone is curious can actually get your memory module out and scan it, see your data, passwords, and all of these perhaps private data. So it increases the attack window, the time for attack. It also has limited write endurance. So for most of these non-volatile memories, you can write the cells limited number of times. So let's say after a million times you write the same cell, it's most likely going to wear out. So it's no longer be programmable or useful. In addition to that, it has a slow and power-consuming write operation. So if you look at the way how these non-volatile memories are made of, typically they are made of certain material that you need to apply heat on it to actually crystallize it or change the material. And because of that, most of the way how you change the state would incur power-consuming and slow operation. So now we understand what persistent memory or non-volatile memory at high level is. Let's now talk about how secure memory in general is implemented. And for this part, it's not related to non-volatile memory. It's in general, whether it's volatile or non-volatile. So before we get into the details, why do we care about hardware security support? Why do we need a hardware to protect the data in memory? First of all, today's computing systems are really highly composable. So if you think of a system on chip, it could contain hundreds of IPs from different vendors. The memory controller is from vendor X, the interconnect is from vendor Y, the core is from vendor Z, etc. So any of these components, if it is compromised, your whole system actually is compromised. So the attack surface is extremely large. Second thing is that even if we happen to know that, well, our friends in Synopsys do their due diligence on verifying their IP security, we want to avoid vendor lock-in. So most system integrators want to have the ability to select from a wide range of options than having vendor lock-in or restrict their options to certain vendors. If there is company or X or Y claims excellent performance numbers and energy efficiency, etc., I want to select their IPs irrespective of which vendor it is. Also, the new computing paradigms like cloud and edge computing. If you think about it now, you could have your payment transactions or your healthcare data being processed in maybe thousands of miles away. In perhaps a data center that you don't have physical control over who is entering it or exiting it, who is doing the maintenance, where this motherboard that you bought came from. All of these details, the memory modules that are plugged in the system, you don't know and you don't have control over. So this also increases the attack surface. Also, we have increasingly usage of proprietary data and models. If you think of deep learning models used in autonomous cars, etc., these most likely will be in your memory module. So if we don't protect those and encrypt them, then it's possible that someone actually can steal some of your perhaps most profitable or financially sensitive data. In addition to all of that, commodity processors, including commercial off-the-shelf GPUs and processors, are increasingly being deployed in safety-critical systems. So increasing the security level or protecting the data being used in these commercial processors is going to be of utmost importance in safety-critical systems too. Because of that all, we have data protection rules. So if you are following these type of rules, there is European Union's GDPR and California's CCPA. All of these mandate strict rules and regulations of how you can store your data, process it, etc. And most of the time, these are done actually in software, but with more attacks actually showing up in hardware like Meltdown, Spectre, etc., we expect that in the future you can end up having more rules that even apply to the hardware chips themselves. So if you have not seen this news article called The Big Hack from Bloomberg Businessweek, it showed this small tiny chip. As you can see, it barely fits on one's finger. And this one has been found actually in sensitive motherboards that are used in, some people say it has been used actually in sensitive infrastructure here in the US. But the idea here is that there was a chip in the motherboard that people suspect it has been actually added during the supply chain or during perhaps untrusted motherboard manufacturing stages. And this has been actually used to compromise system, or it's suspected that enabled certain hacks and compromise of systems. Another thing is the memory modules. If you remember the memory module I showed you earlier that was in the corner there that has non-volatile memory, there has been research that showed that some of these memory modules could contain wireless communication capability. And most likely you cannot even tell the difference. It's going to look exactly the same. You plug it into your system. You think your system is air-gapped, not connecting to the internet. No one can exfiltrate the data. But in reality, you might have some of these modules that are vulnerable. And actually, they are sending your data wirelessly off the system. This is important because if you think of military bases or government facilities, most of these systems will be air-gapped, not connected to external network. But now this definition of air-gapped by just unplugging the internet cord or disable any internet access is no longer the case, because you could have modules that wirelessly send data outside that air-gapped or boundary. All right, so with all of that, commercially, many vendors, what they do is that they follow this strategy. Minimize the amount or the number of trusted components in your system as much as you can. So if you look at the left side here, this is your typical laptop or my laptop. The trusted compute base includes everything. I trust that my operating system is not compromised. I trust my processor is not compromised. I trust my I/O devices, including my keyboard, mouse, My hard disk drive controller, all of those are not compromised. I trust my memory modules. So if any of these components is compromised, has been replaced through the supply chain, then my whole system is compromised. Now, with a little bit more conservative or more secure system, you are trying actually to exclude some of these pieces from the trusted compute boundaries. So if you look at this figure here, what it shows is you are reducing your trusted compute base to only trust the processor chip itself, the operating system, and the hypervisor. Now, everything outside, including the motherboard, I/O devices, memory bus, memory, is not trusted, which means that you need to protect the data once it leaves this trusted boundary and verify it when it gets back again here. Now, even more conservative approach would be actually to reduce the trusted compute base to be as limited to the processor chip. So your application does not need to trust the operating system. It doesn't need to trust the hypervisor. The processor itself provides some mechanism to verify the correctness of execution and the data protection and isolation. So even if you have hypervisor or operating system that is malicious, that is trying to access your application's data, it still cannot do that. And this is more applicable to cloud environments where you do not have control over the hypervisor code, right? If you are working in the government or healthcare provider, you want to process your data in Amazon cloud. You don't know what hypervisor they are using. You don't know if it has been hacked or vulnerable or someone can actually leverage a bug there to exfiltrate your data. And accordingly, you want to minimize what you are trusting in the system. So modern processors allow you to establish trust with the hardware directly and have your processor even protect you from the operating system or hypervisor. Now, obviously, the last two models are what makes sense. This one is definitely not secure or safe if you care about your data's privacy or security. In both of these two schemes, at high level, the processor chip is included in the trusted compute base. And what this means is that once the data is sent out to memory modules or I/O devices, it has to be protected. You have to protect it, which means that it's encrypted. If someone tries to read the data, they cannot actually interpret it correctly. Second thing is that you want to protect its integrity. So if the motherboard or the memory module is trying to change your data, or it's actually trying to replay a previous operating system that is vulnerable, or play a previous image of your memory, all of that will have to be prevented. Support in commercial processors include Intel's SGX, Intel's total memory encryption with integrity, and AMD's secure memory encryption. Now, we understand this figure at high level, which is really the threat model. Everything outside your processor chip, which is in this figure is Intel's Core i7, has to be protected. The data, once it leaves outside, it has to be protected. And when it comes back, it has to be verified and decrypted. So let's see how we can realize that. So at high level, really high level, this is your typical processor chip architecture from inside. It has cache hierarchy, it has computing cores, and it has memory controller. Now, when the data is being written to the memory, it has to go to the security module first. Then it needs to be encrypted before actually it's written off-chip. Now, the decryption will be the other way around. You need to read the data back again, then you decrypt it before your processor can use it. So this provides us with this confidentiality support that protects our data when it's leaving the trust boundaries, which is the compute core. Now, little bit of even deeper look to understand how this will look like. If you want to implement encryption, there are different ways. One way to do that is to use AES encryption engine. So your block that you just saw evicted from the processor chip going to the security module will be this one. And it has to be fed into an encryption algorithm. And there is a processor key that is maintained in the processor for the whole system. Now, the data will be encrypted using the AES algorithm and then, excuse me, then has to be written down to the memory. The problem of this scheme is, first, as you can see, once you are reading the data back from memory, it has to be actually decrypted using the AES algorithm, which is slow. This can take tens of nanoseconds. So now it's in your critical path. Every time you are reading data from off-chip, in addition to the DRAM access latency or NVM access latency, you have to additionally add this expensive decryption process. Second thing is that it is vulnerable. If you think about it, for the same plain text, let's say it's 0, you're going to see the exact same ciphertext written to different locations in memory. So if the attacker is determined, they can use basically ciphertext analysis. They can look carefully at the frequency of ciphertexts, and based on that, they can relate it to natural text. Think of it this way. If you have a Word document, the word there is appearing actually a lot with certain percentage. So if you have seen like similar percentage in ciphertext, then you can relate it back to what does that mean in natural text. This applies also to images. If you have an image and certain color is more dominant, you can actually quickly reverse engineer or know what does this ciphertext relate to. So to avoid this problem, typically something like a salt is used. So every time you are trying to encrypt a block being written to the memory, you need to use metadata and think of it as a salt or a random value that is reserved for every block in memory, which will be used to encrypt it. So every time you have a plain text, you bring its own counter and address, combine them together, and those are the ones going to be encrypted. Once you encrypt those, you generate a one-time pad that will be simply bitwise XOR to generate the ciphertext. Now, in this implementation, there are two features you can observe. The first feature is, even if the same plain text is written repeatedly to the same location, is going to appear differently because the counter here will be incremented. That is maintained per block. The second feature is that, from security perspective, even the same plain text is written to different locations, the address will be different. And therefore, you will end up writing to completely different value, even though the plain text is the same. From performance perspective, now you can, if you know the address of the request, if you know the counter, then you can actually pre-generate the pad that will be used for decryption. So once you read the data from the off-chip memory, you just do simple bitwise operation. So you eliminated the delays in the critical path because you could pre-generate the decryption or encryption pad just from the address and counter, and therefore you just need to do bitwise XOR operation. All right, so let's get so for the rest of the talk, I will be using this scheme. This is what's used academically, and this is what also has been used in commercial processors that implement secure memory. So we are using counter mode encryption, where for every block in memory, we will maintain an encryption counter that will be used to encrypt it and decrypt it. All right, so let's think of how the system will change with that. So now, every time you are trying to write a block to the memory, so let's say this is the location, once you are trying to write it, you need to encrypt it. But to encrypt it, you need to bring the counter, right? The nonce that you are using in the previous figures. So you first bring the counter, then generate the one-time pad, then XOR it with this block, and then write it to the memory. And that's what completes the encryption. Decryption is almost the same, right? In decryption, well, one thing before we get to the decryption part, you need to increment the counter. Because otherwise, if you don't increment the counter, if you repeatedly write the same value, you're going to see the same ciphertext. So you need to make the counter changing. Now, if you look at the read operation, it's the same in some way. You have a miss. You need to read this location. Before you bring the data or the ciphertext encrypted in memory, you bring the counter, and the counter will be used to generate the one-time pad. And when you bring the data from memory, you just simply need to XOR it with the generated one-time pad to complete the decryption. So as you can see, there is a lot of memory traffic now. Every time we have to do encryption or decryption, we need to go to the memory, bring the metadata that correspond to the block we are trying to read or write to complete the encryption or decryption. To minimize that, typically a counter cache is used, which basically caches the most recent metadata or counters. near the memory controller. So if we are trying to decrypt a block that its counter already is cached here, we can avoid fetching it all the way from the off-chip memory. So that can improve the bandwidth and performance. Now, data integrity is another aspect, which is perhaps many of you heard of message authentication codes, right? If you have a file, you want to detect that its integrity is intact, you need actually to calculate a digest or a signature for the data, and then compare it with what was provided to you. So if you think of it, there is a MAC algorithm, message authentication code algorithm, that has an authentication key. You provide it with an input, which is a data or counter block. This is a 64 byte. And then you will generate message authentication code. Now, if an attacker is trying to make up a data block, since it doesn't know the key, it's not going to be able to generate the message authentication code that can actually pass the verification. So when you verify the integrity, what you do is that you bring from the off-chip both the data or counter block along with its digest or message authentication code calculated at the right time. And to complete the verification, what you can do is you can try to calculate the MAC based on that data. If it matches the MAC provided to you, then the data is authenticated, because there is no way the attacker could create data and create its corresponding MAC since it doesn't have the key. So what's the problem with this scheme? Anyone can tell me? So this is a scheme that you can authenticate the data. All right, so the problem with this scheme is that replay attacks are possible. So if a determined attacker, they can replay a previous data or counter block along with its previous MAC and still can pass the verification. So it does not prevent replay attacks. So that's the problem of this scheme. So to protect against replay attacks, typically integrity tree is used. And integrity tree looks like the following. So you have the encryption counters I mentioned earlier. These are really the leaves of your integrity tree. And then you calculate a hash over a group of them, another hash over another group of them, etc. And then you hash the next group to create the upper group, etc. Eventually, you will get one hash value. So that hash value is really you can think of it as the message authentication code or the hash value of your whole memory in some way, right? So it's just calculated hierarchically. So your counters part of them are hashed to create a next level, and this part is hashed to create this node, and then eventually you can hash those to create the next node, etc. Eventually there's going to be just one hash value. That hash value is what will be stored on chip to remember the system's integrity or the state of the memory. Now, looking at system perspective here, you have your root inside your processor chip, on chip. You have the counter cache or metadata cache. You have secure memory controller. You have the cache, core, etc. Now, every time you are trying to bring in counters to the on-chip, you need to verify their integrity. And to verify their integrity, what you need to do here is to calculate the hash and see if it matches what is in the parent. But since the parent is also off-chip, you need also to verify it too, right? So to verify it, you need to calculate its hash and see if it matches what is in the parent. But the parent also is amiss. It's off-chip. So that could have been tampered with. And accordingly, you need also to calculate the hash of the parent. Eventually, you will verify it through the root. Obviously, this is expensive. Every time you want to read a block from off-chip memory, you need to do so many steps of verification down to the root. So to minimize that overhead, typically a cache is used to, these can be cached here in the metadata cache. So next time, so last time we brought this block. Now, if you are bringing this block and trying to verify its integrity, we calculate its hash and see if it's in the parent. Fortunately, the parent is already verified. So you can stop here, and you can just see if the hash of this value brought off chip is matching what is in the parent, which you just verified in the previous access. Then you don't need to do any extra work. Your block is verified. Now, this is the verification process. Now, how do we update this integrity tree? There are two ways to update the integrity tree. One way, which is the lazy approach. In lazy approach, if you update a cached counter, you don't need to propagate it all the way to the root. You don't need to recalculate the hash of the parent, the grandparent, etc., until the tree of the root. You can just wait until this one is evicted. When it is evicted, you update its parent, etc. So only when it's evicted from the on-chip cache, you actually propagate it upwardly to update the root of the integrated tree. Another approach is the eager update approach. In eager update approach, what you do is every time you are updating a counter, you need to update all of the path on chip in the caches. So you need to update this, and also the root. The difference between eager update and lazy update is that in eager update, at any point in time, the tree root reflects the state of the memory. In lazy update, it doesn't. In lazy update, the tree root could be stale because I relied on it to be updated only upon evictions from the metadata cache. All right, so now we understand what secure memory looks like. What do we mean by integrity and confidentiality protected memory? We also know what do we mean by emerging non-volatile memory or persistent memory. So what's the story here? Why is it challenging to implement both? So these are some of the challenges we have been looking at, but perhaps the most prominent one here is ensuring a crash consistency of security metadata. Now, as you are updating the integrity tree or encryption counters, you might have updated them in the cache, which is volatile, it's on chip, but the data has been updated off chip, which means that if a crash occurs at any point of time, your data and its corresponding security metadata is not synced. They might be different versions. The data, but the metadata was updated in cache, so upon a crash, you will have your data decrypted using an older encryption counter or a different integrity tree root. There is the second challenge which we found, which is very high security metadata reconstruction time. So you have a power outage now. You know it's persistent memory, which is great. I can recover my data. But at the same time, what we found is you need actually a lot of time to rebuild your integrity tree. If you think of terabytes of memory, to rebuild the integrity tree, it can take you hours, and I will show you why. The third challenge we found is the integrity tree structure is somewhat problematic in highly error-prone environment. If you have errors in the integrity tree, especially in upper levels, those will cover large part of your memory and will render large part of your memory unrecoverable. So that is a problem we have looked at, and this becomes increasingly important in large-scale memory. The fourth challenge we found is the persistent memory applications regularly persist data, right? Think of database transactions. You are updating a database transaction, you want to write it off chip to the persistent medium, the memory. The problem here is that before you do complete this write operation, you need to encrypt the data and update the integrity tree, which becomes in the critical path of persistent applications. We realize that this can take long time and degrade the performance of these applications significantly. The fifth challenge is you have, for persistent memory, some of the processor vendors like Intel, they wanted to simplify persistent memory programming. So what they did is that they included the cache hierarchy inside the persistent domain, which means think of having a battery besides your processor, and every time there is a power outage, that battery will be used to write down all of the contents of your cache hierarchy. So it's no longer that the persistent memory is just the non-volatile memory. Your whole processor chip is considered persistent because you have enough power to flush out all of the data inside your processor chip. What problem we found is that including security operations can significantly increase the demand for this additional energy you need to drain your cache hierarchy. We found that it can be like 8 times more operations that you need to basically drain your cache hierarchy, which means larger battery size. Carbon footprint, environment, all of these problems could arise when you need to do that. All right, so let's get to the first one, which is ensuring crash consistency of security metadata. So this is your typical persistent application. This is a database application trying to update my record. It has to update it in the persistent domain. So first thing you do is that you read the data from your persistent memory. This could be a file or could be database, like structured a little bit different than file. And then you update it in the cache hierarchy. But that's not enough, because if now there is a power outage, this transaction will be lost because this is volatile domain. It's not non-volatile memory. So what the persistent applications like Intel's PMDK library do, the application has to explicitly flush or write back the modified data in the volatile domain down to the persistent domain. So the application will issue a write back or flush instruction that will take the cache hierarchy block down to the secure memory controller. Now, before you write it to the persistent memory, what you need to do is the following, right? You need to encrypt the block and update the integrity to provide integrity protection for the data. So when you do that, you typically update these in the metadata cache and use them to protect this block and then write it to the memory. Now assume there is a crash. If there is a crash, your updates were in the volatile domain, the non-persistent domain, and there is different versions used, right? You have stale values for the counters and integrity tree because those were updated in the volatile cache, but you have your data up to date. So when you try to decrypt this data, it's gonna fail because a stale encryption counter will be used. Moreover, when you try to verify its integrity, you will also fail because the message authentication code or integrity tree information are also stale. Therefore, it broke your persistent application. It broke the persistency guarantees of non-volatile memory. So that's what we call the crash consistency problem between the security metadata and the corresponding data. So how to solve this problem? So this is the first challenge. One way to solve this problem is to naively, or before naively, the requirement here is to recover the encryption counters. So once we have the system recovered, we want to figure out which encryption counters were lost from the cache hierarchy and try actually to recover them or basically bring up their most recent values used for encryption so that you can do the decryption correctly. The second thing is that once you have got back your encryption counters, you need to rebuild the integrity tree. Because remember, the integrity tree is built on the encryption counters. There are naive ways to do that. If you think of making sure that your encryption counters are up to date, the cheapest way to do that is every time I'm updating a block, I update its encryption counter all the way in the memory. But the problem here is obvious. It's like a write-through cache. It's gonna double the write bandwidth every time you are the write bandwidth consumption. Every time you are writing a block, you need to also write its counter to the memory. So let's get to understand how this works. The naive approach, which is using metadata cache or counter cache that is write through. Every time I'm updating a block in the counter cache, I need to update it in memory too, which means that every time I'm updating or writing data to the memory, I need to update its counter persistently all the way down to the off-chip memory. That will consume twice the memory bandwidth. Whereas the write-back policy, which is typically used in processors caches, only the block when it's evicted and it is dirty, you actually have to write it back to the off-chip memory. So with that gap you see here between 200 times the bandwidth and only 5%, this one does not provide crash consistency, this one provides crash consistency, but there is a large gap between them in terms of the write bandwidth consumption. So how do we bridge this gap? So if we want to divide this mission into two parts, the first part is first identifying which of the counters in the memory are stale. That's the first part, right? The second part is these stale counters, what was their most recent values in the counter cache? And fix that, bring it to the most recent counter cache value. So these are the parts you need to, this is your data there in the memory after a crash. You have also your counters. You need to identify which of these counters were lost in the counter cache because of it being volatile. And then you need actually to be able to bring them to their most recent values was used to encrypt their corresponding data. All right, so the problem with this one is that even if we use eager update integrity tree, it is actually likely that you cannot recover from this crash, because now you have multiple of them lost. It's large computations to actually come up with the right combination that gives you the correct route. So how to solve this problem? So our solution, which was published back in Micro 2018, was built on this observation that your error correction codes, and error correction codes are perhaps just small codes typically used to correct errors. So if there is a single bit flip in your data, if there is any error because of a jitter, silent data flip, etc., all of those will be detected by typically error correction codes, or most of them, unless the errors are so severe. And typically these are stored along with the data. So you have a plain text, you calculate the error correction codes, and you are encrypting this whole thing as part of your ciphertext and write it to the memory. So what we found is that these ECC codes serve our purpose of recovering the counters perfectly, because when you complete the decryption, you will bring the counter from the off-chip memory, this is after a crash, and try to complete the decryption. Once you complete the decryption, you will get plain text and ECC. If the counter used was stale to decrypt a more recent data that was not encrypted using it, the result here will be completely random, which means that most likely your error correction code will show errors, and hence you will detect the problem. Now, is this the only time you will have problems in ECC when you use the stale encryption counter? What if you had error, actually? How can you distinguish between them? Because if you have your error correction codes indicating a problem in the plain text, it could be simply because your decryption was done wrongly using a wrong counter or a stale counter. But that's not the only reason. It could be actually an error. You could have had bit flip in the plain text and your error correction code detected that. So how can you distinguish between those? So what we have found is that natural errors, even if it's a very harsh environment, would not lead to so many bit errors within the same block. And therefore, what we do is we use the count of code words within a block that are showing errors to indicate whether it was because of wrong decryption or actual bit flips. Without going through the proof or the reliability analysis, that's something you can check on the paper. Now, the design has changed a little bit, which means that in the read operation now, you do the decryption, you obtain the ECC, etc. This is during runtime, so we don't do anything during runtime. Only upon recovery from a crash, we do the extra work that Osiris does. On write operation, we do the following. We do the ECC encoding of the data before we complete the encryption, so that this ECC will be used as a sanity check for the correction of the decryption process. In addition to that, this part I have not described, which is we don't want a big divergence between the counter value in memory and the most recent counter value on chip, because you need to try a lot. You need to try keep incrementing the counter. Once you recover from power outage, you need to keep incrementing your counter many times before you get ECC that is meaningful. So this could be unbounded, could be like millions of times, right, if you are not careful. Therefore, what we have done is that we limited this divergence by every nth update to a counter, you need to persist it. And hence, this n is the divergence factor. So between the value in memory and the value in the counter cache, there shouldn't be more than, let's say, 16 values. And therefore, you need to only try up to nth times before you recover the actual value. So without going through more details, by doing that, we were able actually to eliminate most of the overheads. And in fact, we were even able to do better than the write-back policy. So if you look here, we have had the number of writes, which is important. If you remember, NVMs have limited write endurance and the slow write operations. So what we had here is we reduced the number of writes from write-through, which is 200 times bandwidth consumption, to, in some case, less than the write-back policy, and in some case, just slightly higher than the write-back policy. Without going through the details of these two versions of the implementation and their trade-offs, I will leave it at this. The performance as well, we were able to match the performance of write-back policy, but ensuring that our system can recover the counters after a power outage by leveraging this ECC as a sanity check to recover the correct counter. Now, what is the problem of this scheme? The problem of this scheme is that to recover the counters and rebuild the integrity tree, you need to iterate over all of your memory, go check the ECC for every data block, recover its corresponding counter, and then build your integrity tree. If you think about that, this is extremely expensive because now your memory could be terabytes of memory. So some of these non-volatile memory-equipped systems, Xeon servers, had 6 terabytes. Imagine that every time there is a power outage or you restart your machine, you have to iterate over 6 terabytes and check their ECC. And then you have to build your integrity tree. So how to solve this problem? One way to solve this problem is that every time I'm updating data, I update all of its integrity tree path, the counter in memory. This gives you how much recovery time? 0. Because at any point of time, your integrity tree, your counters, and data is up to date. But the problem is that the overhead is high because every write operation to the memory now will incur almost 10 additional writes. This includes the integrity tree path and the encryption counter. On the other hand, if we want to use the Osiris scheme, which I mentioned, you need to iterate over your memory blocks and build the integrity tree. Now, as your memory size increases, and this is actually the sizes we have seen in the demo servers by Intel, it can actually take hours just to rebuild the integrity tree. So how do we solve this? How do we bridge the gap? So one solution we have looked at back in ISCA 2019 was to, rather than persisting the whole integrity tree, we could actually just persist some part of the integrity tree. For example, by just persisting the data block and the counter, we can actually quickly build the integrity tree because the arity is high. It's 8 times multiplied by 64 times, so it reduces the recovery time significantly. But at the expense of what? Extra writes. Every time I'm writing data, I need also to write the encryption counter corresponding to it also in memory. To reduce even the recovery time further, rather than just the counter and the data, you can also additionally persist the parent first level of integrity tree. That we call it Triad NVM1. Triad NVM2 actually persists the first 2 levels of the integrity tree in addition to the counter and data block. So if you think of this, there is a clear trade-off. Strict persistence incurs very high overhead, as you can see, but it provides you with immediate recovery. You don't need to rebuild anything. Your metadata is always up to date. On the other hand, a scheme like Triad NVM1 reduces the overhead, but has high recovery time. It takes almost 4 minutes for an 8 terabyte memory. Triad NVM2, because it persists more of your integrity tree path, would take a higher hit, which is 10% performance overhead in performance, but it will reduce the recovery time to 0.5 minutes. Then Triad NVM3, which is even persisting longer part of the integrity tree path, will be taking 15.6% performance overhead hit, but reduces the recovery time to almost 4 seconds. So this is the main trade-offs here. So this solution is boring, right? I mean, it's typical Pareto frontier figure where this is strict persistence. You persist the whole integrity tree path, but it gives you low recovery time, but very high performance overhead. On the other hand, we have the Osiris scheme, which is going to give you low performance overhead, but recovery times in hours. Then we tried to do like this trade-offs in between. Okay, well, can we reduce the overhead, but actually increase the recovery time, etc., until we reach to Osiris. So what we ideally want is something here. And that's what our next work is proposing. So we have a work called Anubis. And what Anubis really proposes is you don't need actually to iterate over all of your memory to rebuild the integrity tree. If you have a mechanism to remember which nodes could have been lost, you only actually need to go to them and fix them. You don't need to iterate over your whole memory and rebuild it. To do that, we defined a small shadow table that is as large as your counter cache or metadata cache. And every time we are having a miss and bringing a block, we actually log the address of that block in the shadow table. Now, your shadow table will be like a logbook that remembers what was in the cache, before, not the content, but the addresses, before a crash. And why this is not high overhead? Because most of the time you bring the block and use it many times. The only thing you do is actually log the address only when you bring it. So it's depending on the number of misses you have in the counter cache, which is typically a small percentage. So now, once you have a crash, and recovery from that crash, you have a list of the addresses that could have been out of sync. They have not been actually up to date because they were updated in the cache. And what you do is you need to use Osiris to correct the counters, and then you rebuild the integrity tree based on that. Eventually, you will get the most up-to-date root value and can compare it with the root value you have on chip. If it matches, you were able to recover your system correctly. So Anubis here is providing, here I'm comparing it against the baseline write back, which does not provide recovery, versus strict persistence, Osiris, and the two versions of Anubis, which is Agit Read and Agit Plus. Without going into the details of those, the strict persistence one is extremely bad in terms of performance, but gives you low recovery time. Whereas Osiris, remember, it was very high recovery time, which is hours, but it gives you very low overhead. So Anubis provides this interesting trade-off here, but it's both low in terms of recovery time to less than 0.5 seconds, and the performance overhead is only 3.4%. So this was what Anubis does. Now, the third challenge which I mentioned is that if we have an error in this part of the integrity tree, a data error, you just have a jitter, high energy particle, or something that actually flip bit into this data that it's not corrected, it cannot be corrected, then any data that is decrypted using this counter block cannot actually be corrected. So this covers 4 kilobyte region. If this becomes uncorrectable, then you lost 4 kilobyte of the data covered using that block. Now, the problem becomes if you have errors in even higher levels of the tree, they cover much larger memory. If this one becomes faulty, then you cannot recover or verify the data actually under it, which is 1 gigabyte, which means that errors in integrity tree could render a large percentage of your memory unrecoverable. So this is a reliability analysis we have done. The x-axis is the uncorrectable errors per gigabyte. So here we are varying the harshness of the environment, whether it's a space shuttle or whether it's a car or your own laptop. How often do we see or incur errors that are uncorrectable? For a secure memory, you can see it's much higher unverifiable data than uncorrectable error. The general memory. Because in general memory, when there is an error, only that data will be impacted. But if it's secure memory, if there is an error and it happened to be in the integrity tree, it covers large percentage of your memory. So that's the problem we have been looking at. And one interesting insight we have had is updates to the integrity tree. So the importance of the integrity tree levels goes this direction. The higher you go, the closer you go to the root, the more is the impact of the errors, the more it covers, right? Because it's a tree structure. The lower you go in the integrity tree, closer to the leaves, the less it covers, and hence the less it impacts the system's availability. What we have found, interestingly, is that the number of writes is the opposite, or the trend of the number of writes is the opposite. So you have much more writes for lower levels than the higher levels, close to the integrity tree root. And we leverage this insight to duplicate or even have multiple clones or copies of the higher levels of the integrity tree. Since they are written not frequently, you can actually duplicate them without impacting the performance significantly. So we have this Soteria relaxed decloning and Soteria aggressive cloning. I will not go through the details of them. But the Soteria scheme incurs minimal overhead. As you can see, it's less than 1% overhead, but at the same time, it provides you with the same reliability as in conventional system versus secure memory system that is oblivious for error correction. Now, going to the fourth challenge, again, persistent applications have to persist or flush the blocks from the cache hierarchy down to the persistent domain. What Intel did to minimize the overhead, because that takes long time, they included the write buffer in the memory controller, which is called write pending queue, into the persistent domain. So now, instead of having to flush a dirty block all the way to the memory, you can actually just flush it into the write pending queue, and then it's considered persistent, because even if there is a power outage, your battery will be sufficient to actually flush back, or the capacitor is sufficient to flush the contents of the write pending queue. Now, the problem here is that, so this is great, it saves a lot of performance, reduces the latency for persisting data. But if you add security module and trying to protect the data before it goes to the persistent domain, it becomes a problem. It really defeats the purpose of this whole ADR support. Because now, every time you want to evict a block or write it to the persistent domain, you need to add all of these overheads for encryption and for integrity metadata calculation, which means that your data is actually delayed significantly before it's considered persistent. So adding this internal buffer does not add much value. Now, how to solve this problem? Let's look at the trade-offs here. So this is the baseline system, which has security module. Now, if the persistence domain without any Intel support is outside the processor chip, it requires no backup power. You don't need battery, but it has slow data persistence, because every time you are persisting data, it has to be written all the way to the memory. On the other hand, if you have the ADR support deployed naively, then what you have here is, since your data is persisted in the write queue, once you have a power outage, you need to protect the content of the write pending queue, and this can take long time, and hence it also needs higher battery requirement or residual energy requirement. On the other hand, if you want to keep the same small battery, you want actually to do these security operations before you buffer things into the write pending queue or persistent domain, but obviously this will slow down the persistent transactions, but it will require a small ADR budget. And there is a clear performance gap between them, as expected. So in Dolus, what we found, and this was published just last year in Micro, what we found is that you can protect the content of this buffer using a small minor security module instead of the security unit that protects the whole memory. So as soon as you write a block into the memory, you don't need actually to do the integrity tree update, etc. As long as it's in the right queue. You just protect it using smaller integrity tree data structures. Now, another aspect is that we can pre-calculate the encryption paths and integrity tree, because you only flush the write queue once when your whole system is recovering. So you don't need the freshness guarantee for every write to the write pending queue, because it's on chip. So with that, we have a draining path that is secure. If a crash happens, your write queue is already safe. We don't need to go through the security unit, which means that we can live with a small battery size. And meanwhile, if we are at runtime, once it's evicted from the write queue, it's protected using the major security unit, which covers your whole persistent memory. So by this decoupling, we could actually achieve performance improvement that is 1.66x than the baseline. Now, another aspect, now Intel get a little bit more greedy, and they have the persistent domain not only including the write pending queue and the memory controller, but it's even actually more conservative to include the whole chip. So if you update anything in your cache hierarchy, it's considered persistent. It can be written back to the memory. So the problem here is that when do you protect your data now? How do you do that? The idea here is that now if your dirty block is being actually drained after a power outage event, you actually now need to add all of these security operations before you write it, which means that you increase your your battery size significantly. As you can see here, if we have no security, this is the maximum number of operations we need to memory. But if we have security enabled, we could actually have much more memory operations, which includes integrity tree update, encryption, bringing encryption counters, updating them for every block in the cache hierarchy, which will increase the number of operations significantly, and that translates to an increase into the battery size. Now, this is the design. We dedicated an area in non-volatile memory that just you flush your cache hierarchy into that area instead of writing them down to their in-place locations in memory. By doing that, we're able to provide compact protection for the cache hierarchy content. We were able even to pack the message authentication codes and all of these parts to reduce the number of writes. In summary, we're able to reduce the amount of energy needed to drain a cache hierarchy in a secure system by almost 8 times, which is a result from reducing the number of MAC operations and the number of writes to the memory, or the memory operations in general. All right, so I think with that, I will get to the ongoing research projects. I think we are doing quite okay in time. So one project we are looking at now is, in today's computing systems, we have high-performance computing nodes typically that are coupled closely with memory modules. Future architectures are featuring something different in the sense, okay? So in the sense that your memory is centralized, put in a centralized blade, and your compute nodes can access this global shared physical memory. So where and how do you implement security protection? How do you implement access control are all of these active research areas that the industry and the academic community are looking at. Also, we are looking at how we can implement efficient security for system on chip. So you could have hundreds of different IPs come from different vendors. Can we potentially employ untrusted IP or design securely? And that's the question, is if we have a memory controller that is not trusted, can we use it but still have protection to check that it's doing its job correctly? This applies to almost any other IP. Is this possible? I think this is highly philosophical question that we are still trying to formalize and understand. The last one is we are looking at how we can simulate systems where we have detailed RTL model, where other higher level, more abstracted models, how we can implement this simulation infrastructure efficiently, how we can minimize the simulation time, how we can potentially capture the simulation model more efficiently such that even very detailed, let's say RISC-V processor is used while we are still be able to achieve the simulation speed we use in GEM5 or any of these simulators. All right, so with that, I come to conclude my talk. So first, we discussed how integrating NVM while supporting secure memory introduces challenges. Memory security implementation impacts the system availability, the energy requirements or backup requirements. It impacts the performance. It impacts the reliability. And hence, we have to be careful when we adapt secure memory implementation to new technologies and architectures. Adapting memory security to new architectures is challenging. That's something I think by now all of you understand. Also, future systems will deploy components with various trust levels. You could have your memory controller somewhat trusted, this is trusted. So how do we design an overall holistic secure architecture considering this various trust models? And finally, the availability of open source designs might enable more realistic design space exploration and architectural simulators. How can we make this efficient and take advantage of available real implementation and integrate them into our simulation models? With that, I would like to first thank my students who have been working on many of these projects and contributed significantly, and I will stop here to take any questions. Yeah.
It's a very interesting talk. Although I'm not familiar with the field, I have some background in Kansas State and stuff like that. So my question is, what about improving the memory technologies itself security. I'm not familiar with your field, but this is just
Yeah.
my background in transistors and some classes I took on that.
Yeah.
Thank you very much.
Yeah, so this is really a double-edged sword, really, in some sense, right? So first of all, using these type of technologies that have longer retention time of data would increase the attack window, right? Your data is staying there unencrypted for a long time. Even when you discard your system, your data is there. So from that part, it's vulnerable. Now your question is, can we use the non-volatility or persistence or characteristics of these technologies for even helping us implement security features? Is that the question? So there have been researchers looking at that. So for example, some people were looking at one-time programmable non-volatile memory to ensure some sort of system integrity. So every time you are encrypting a counter or etc., it's persistent, it's one-time programmable, no one can actually tamper with that. So there has been researchers looking at using RAM in that context. There have been also researchers looking at using non-volatile memory inside a trusted platform modules. So if you have a chip that is responsible of storing your security credentials, including your encryption keys, your certificates, etc., inside that chip, they have been looking at leveraging non-volatile memory to make it always remember this information, such that no one can actually remove or erase these valid certificates or most recent update of the system. So I guess it has been used in that context too, but also the way how we use some of the resistive RAM, which you referred to, is to enable in-memory computing, which brings in, from architecture perspective, a new security challenges of when and how do you implement the data protection schemes. So all of these apply, so that's a good question. Yep. All right, any other questions?